have to confirm. Oh.
Okay, so welcome to our special Diwali seminar, and it's good that you have come despite our festival today. And yeah, today's talk would be by Hans Jockers from Mainz, and he's going to talk about his recent work connecting JT gravity deformations and topological topological recursions and things. Okay, so over to Hans now.
Okay, thank you. Thank you for the organizers for this invitation to this seminar. And I must say, it's a great title, The Dual Mystery Channel of Gauge and Gravity. I like it. So it's a pleasure to be at least virtually in Madras. I wish I could be there in person, but well, not in these days, I guess. Okay, so I will be reporting on some work that I'm doing with Stefan Förster from the University of Bonn, and also with Joshua Kames-King from, also he's a PhD student of Stefan Förster, and he's actually a very talented PhD student who is on the market this year. And then there's also my PhD student involved in this, Alexandros Kanagias. He's a second year, just started his second year. And this work I'm mainly reporting on has appeared on the archive, and there's also some work in progress. So there's a brief outline of my talk. I will give an introduction to the subject, then I'll talk about where we have mainly made, or where we have made contributions, namely how we believe is a good strategy to describe deformations in this context by looking the relation of these partition functions that will show up in the context of the Kdv hierarchy, which has appeared in the context of topological strings. And then I'll depending on how much time I have, I'll talk about some applications and some outlook. So let me start with the introduction. So the key player in this game is going to be Euclidean, the Euclidean JT gravity action. Check if Teitelbaum, gravity action. Which takes the following form. So there are a bunch of terms that I will spell out, and others that I will just not spell out. But the important term is going to be this term, where you have almost like an Einstein-Hilbert term, but the additional ingredient is that you also have in this theory a scalar field, which couples linearly to the scalar curvature R. And then we actually modify this a bit. We also add just a linear term in the scalar field. And then we have a topological term that we would like to include, which is the Gauss-Bonnet term, which is just essentially the Einstein-Hilbert term. And then we have various boundary terms. If we are looking at some two-dimensional manifold, where we also allow to include boundaries. Okay, so the boundary terms comprise one part which actually makes this into the boundary Gauss-Bonnet term. So there's a boundary contribution, and another part which describes the dynamics of these of the scalar field at the boundary. This is given in terms of a Schwarzian, which is also a very important term. But for the purpose of this talk, I don't need to spell it out explicitly. So what does this action do to us? Well, first of all, if you look at the equations of motion with respect to phi, that's the usual story, then this gives rise to a constraint, which essentially forces the scalar curvature to be negative. So this constraint actually forces the metric to be hyperbolic. So we are looking at hyperbolic geometries. And the other term, as I said, is a topological term, which will also be important for us. So this is just essentially giving rise to the Euler characteristic of that Riemann surface. Okay. Now I mentioned that we have the scalar field, and I mentioned that we may allow, or that we will have boundaries. So at the boundary, we need to impose boundary conditions, and the typical boundary conditions imposed in this game, that we have some asymptotic boundary of the following sort. Then at the boundary of that scalar field, we actually require that this scalar field approaches 0. And I want to do that in a way that I will do that in a regularized fashion that will become clear in a moment. So we introduce a parameter, a parameter epsilon in the following fashion, and that the length of the boundary, which actually becomes infinite. So this is how we regularize that boundary at an infinity. These are the boundary conditions. And if you do that, then we can actually now compute a partition function. So we have now these geometries, and here I illustrate one with one boundary component. This will be the cube layer for this talk. So this is supposed to be one of these hyperbolic geometries. And let's have a look at some higher genus situation here. And then we describe in the bulk there we have this JT gravity action that we talked about, where I spelled out the bulk terms. And then, like I said, there are also some boundary contributions which describe the boundary degrees of freedom here. In particular, there's this famous Schwartzian of this scalar field, which describes the dynamics at this boundary. Now, in the seminal work by Saad, Schenker, and Stanford, it was now realized that that if you compute this JT partition function, which depends on this quantity beta, and where we sum over contributions of various genera, that this is actually dual in the sense of an ADS CFT correspondence, CFT1 correspondence to what is an ensemble.
Hans, I have a question. If R equal to -2, how can genus 0 and 1 work?
Okay, so you're asking good. Okay, so you're asking because it's as a stable it's not a stable curve. That's your question, I guess.
Yeah,
right?
in some sense, because chi of 0 and
yes,
1
so these
is
are certainly
-2 is
yes.
+2 and 0.
These are certainly special cases. However, okay, you have to be very careful what kind of boundary conditions you impose. So certainly at genus 0, you can have that kind of asymptotic boundary condition. But what you can't have is you can't have a disk where the boundary is a geodesic. And it's this part where you have these geodesic boundaries, which relates to the stable curves in topological gravity. But you can have a disk with such an asymptotic boundary. There's nothing wrong with that.
Okay.
And similarly, you can have a genus 1 curve. Well, as you can have a genus 1 curve with a marked point, you can have a genus 1 curve with one geodesic boundary, and that's also fine. I'll get back to that point actually in a bit, but did this answer your question for now?
Yes.
Okay, so what it describes here, it's an ensemble of quantum mechanical Hamiltonians or quantum mechanical systems, which is given in terms of a double-scaled matrix integral, which now also depends on this beta. And the kind of ensemble of Hamiltonians we are looking at is the following: that there's a certain measure, and the measure characterizes the particular class of matrix models. And then we are looking at this integral over Hamiltonians and this usual insertion of e to the beta h, and taking a trace over this is a typical form of such an ensemble average of Hamiltonians. So what should be stressed and what is maybe interesting in this context, in this duality, is that we have a theory here, namely this JT gravity with this action, and this is in this proposal dual to an ensemble of quantum mechanical systems. Okay, so now we come back to this question Suresh was actually raising. I will now in this talk mainly focus on this side, although this side can also be discussed, and we do that in the paper. So you can evaluate this side with standard matrix model techniques. And the nice part is that also on that side, you can actually explicitly compute these various ingredients, as has been noted by this very interesting work here. So let's start at Genus Zero. So Genus Zero, as was pointed out, is kind of special. And actually, Genus Zero has been computed already previously. So you can just localize on a disk. And what it localizes to is this, what I haven't written out. You can evaluate the path integral exactly by looking at this. So the dynamics come from this boundary Schwarzian, and this can be carried out exactly. And this has been done a while ago, and it will give such a characteristic contribution where you can also interpret these various powers of beta, which, by the way, I should have mentioned, has the interpretation. It's this closed circle in Euclidean field theory has an interpretation of inverse temperature. And this one has been, for instance, first pointed out that this can be computed by Witten and Stanford. But now the interesting part is that we can also do this computation at higher genus. And this is where this question of Suresh comes in. So what we need to compute is actually, we want to compute the volume of the moduli space of these hyperbolic genus G Riemann surfaces with this discussed boundary condition characterized by this beta. And this is now done typically in the following fashion, as was noted by SSS. So let me abbreviate this SSS. So we can do the following. We can now cut the surface along a geodesic closed curve. So cut along a geodesic curve. And then there are two contributions here. One is called the trumpet. And the trumpet depends on the length of that geodesic curve, which I note by B, and at the length of this asymptotic boundary as beta. Okay. So here I should say this has length B. And then there's a piece, then there's a second piece, which I denote by the volume of the moduli space of such hyperbolic Riemann surfaces with such a geodesic boundary condition. And this also, for one boundary, depends on this this volume of this moduli space also depends on this length beta. And it's this quantity here where you must be careful. You can't have this, for instance, you can't have this at Genus Zero with one boundary condition. This is just empty. So in other words, what I'm trying to say here, I mean, to illustrate this, I mean, take any hyperbolic two-dimensional space, and certainly you can cut out a disk. I mean, there's nothing wrong with that. But if you want to impose some constraints on what kind of boundary you want to have, then certainly not everything is possible. In particular, what is not possible, you cannot cut out a disk where the boundary of that disk is a geodesic curve. But what you certainly can have is you can have these asymptotic boundaries at a disk. Okay. Okay, now since we have this cut in half in the following fashion, we then can now do the computation in the following way. Well, we integrate over all, I mean, in order to figure out the moduli space of this whole thing that we're interested in, we integrate over all possible geodesic length, dB. Now you must be careful. This is not quite the correct measure yet, because it's not just that we need to integrate over this length, but you can also start twisting how you glue that trumpet piece to that part of the Riemann surface. And this taking this also into account, so we must, for a particular length b, we also must do all the twistings, the possible twistings, which gives another, if you think about this, gives another factor of b. And then, so this is now the measure, the cluing measure. And then we get the wanted result by taking now this trumpet piece, which depends on b and beta. And then we can multiply it with this this volume of the moduli space of this remaining piece with this geodesic boundary. Okay, so why is this a good strategy to do? Well, this is a good strategy to do because
did you tell us
yes.
why the formula Zg equal to volume holds? Did you tell us that?
Why this?
And the partition function is the volume of this moduli of I mean of this space, the volume of that space.
It's the volume. It's the volume of the. It's the volume of the moduli space.
Yeah. How do we see that?
So okay. So you want. I mean, what is this partition function doing? This partition function is. So if we want to essentially count all possible geometries, right? And how do I count possible geometries? Now I have a continuum of geometries, and a good measure for all possible geometries is going to be the measure the volume of these moduli spaces. So at a given genus with a given boundary beta, inverse temperature beta, we want to count those. Okay, and then there is this factor, this topological contribution coming from this piece here. Now we localize on these hyperbolic geometries, and now so the volume of these moduli spaces is essentially the multiplicity, the multiplicity of the geometries. So this is
okay, I got it.
Yeah.
Thank you.
Okay, good. This is why we're interested. Well, we're interested in this module. Oops, we're interested in this moduli space, and we're decomposing it into the moduli space of this part, and into this moduli space of this universal part, which again can be calculated rather easily. So we are down to the problem of looking at these. Okay, so you might ask, why is this a good strategy of decomposing in the following fashion? And this brings me now to the main part of this talk, namely to the Kdv hierarchy. And the deformations. So it's a good strategy, and I should say this strategy of relating it to the Kdv hierarchy, or more particularly to the topological gravity correlation functions. This has also been used by Okuyama Sakai in very interesting series of works, which have been also very inspiring to us. Should give credit to them here. And so the essential input goes back that actually these moduli spaces here, this volume of moduli spaces here, they have a connection, a direct connection to topological gravity. And this is something that has been by this very important work by Mirza Kahani on this topic. So she realized that these moduli spaces of these, the volume of these moduli spaces can be actually calculated in the context of topological gravity, or in the context of the moduli space of stable curves. So essentially the statement in our context with bound boundary is that you can compute this by integrating over the moduli space of stable curves, in this case of genus G with one boundary. And what do you need to integrate? Well, you need to integrate a characteristic two form, which is the Weil-Petersen two form. And if it were a surface without a boundary, a hyperbolic surface, this would be the end of the story. But then we also need to take into account the information which comes from the boundary, and this is shown to be taken care of by including the following psi class in the following fashion, where psi1 is now the first Chern class, of the line bundle, the cotangent line bundle on this moduli space. So this is the cotangent line bundle on the moduli space of stable curves. So how can you think about this? An element of this moduli space of stable curves is a stable curve, and you have a marked point. At this marked point of this stable curve, you have a cotangent line, and you pull this back to the, for this particular member, and then you build a line bundle on the moduli space of stable curves by essentially taking these lines at every element, which is this curve, and this patches to a line, and you take the first Chern class, and this is what this characteristic class is. Now, the insight is that you can now compute these volumes by carrying out such an integral on this moduli space of stable curves. And now comes this thing what has been asked before. So obviously, this moduli space of stable curves is only defined if the genus is high enough or the number of markings is high enough. And so this is in a very nice one-to-one correspondence. These hyperbolic Riemann surfaces with geodesic boundaries also only exists if this conforms nicely with the same condition that you would impose on the moduli space of stable curves. Okay.
Hans, this formula just means you expand it and take the top form, right? I mean, that's all.
Exactly. So this, yes. So this just since you expanded the top form and you integrate over it, and this is a correction that you get due to the presence.
You'll get mixed terms. That's
of the boundary. Yeah, that is right. Mm-hmm. Okay. So now there's a generating function of topological gravity correlators. And this, this goes back to this very old work and very important work by Witten and Kontsevich. Well, so this generating function depends on some parameters tk. And what is it? Well, it's the generating function we sum over all genera. And then we have here, this is a horrendous sum TD to D, some genus G. So there's a formal variables taking into account the genera. And this correlation function is a shortcut for having various insertions at marked points. So what is this tau D? This tau D is essentially very related to this psi class that I introduced already before. However, we take this now to the dth power. And then if you expand this out, what this means is every tau D corresponds to an insertion at a marked point. This is why I've written now here I. So I labels the different marked points. And depending on how many in this expansion, how many tau Ds you have, so many marked points you should consider in that particular stable curve geometry. And you package this all together in this function f t of k. Okay, so the nice thing now is that this generating function connects directly to the generating function of JT gravity correlation functions. So there's a generating function of JT gravity. Well, they haven't traced it in this form, but this has been noted by, in the context of Mirza-Kahani's work, this has been noted by mathematicians, by Liu and Xu, but then also Molasse and collaborators. And in the physics context, there's also a nice exposition on this by Dijkgraaf and Witten. And the upshot is that this the corresponding generating function, which I denote by G, depends on some parameter gammas. Tk is essentially given by the same generating function, but just with a simple shift, where the gamma k's are constants. So gamma 0 is 0, gamma 1 is 0. So there's a bit of an anomaly in the beginning, but then gamma k is -1 to the k. And these constants for higher k's, they get factorial suppressed. So this is for k equals 2, 3, and so on. And the nice thing about this generating function is now that these volumes that we're interested in, well, not just these volumes with a single geodesic boundary condition, but I spell it out now for these particular volumes, they can be obtained by taking this generating function and taking, with some decorating factors, by taking derivatives with respect to these parameters dk, and then setting the tk is equal to 0. Okay, so what I'm telling you is that we have a very comprised form now. So we have this generating. Okay, so we have this generating function. From this generating function, we can define a new generating function, which is very simple because it's just related by such a shift. And then we can get all these volumes in terms of this generating function, or I should say, picking out particular terms, decorated with the information of the length b here. And now you can go ahead and essentially take this formula, plug this into this expression, and get expressions in terms of this generating function for these volumes that we're interested in. Okay, this can be done, and you do it in the paper, but it gets a bit messy and technical. But what I would like to stress here now is that this is not just any function, but this is a particular function. This has been noted by Witten and Kontsevich. It solves what is called the Kdv hierarchy. So what's the Kdv hierarchy?
Can I ask a question? Hans,
yes, sure.
That? I haven't read the Liu Zhu papers or Mandase, but Dycraft and Witten, I remember reading it. And so this would be the case of pure topological gravity, right? Without matter. So because they had done more general things.
Yes, so so I don't know precisely remember of what they discussed in Dycraft Witten.
They did minimal models, topological minimal models coupled.
So they might not have included a boundary. That's what you're saying.
Yeah, they did. I don't remember boundary either.
Okay,
yeah.
So certainly, I don't also now remember top of my head what precisely they discussed there. They did discuss this on a slightly different level, namely. Certainly, for sure they discussed the case when this term is not there, and then it boils down to expressing these Weil-Petersen volumes in terms of these other characteristic classes, which are discussed in the context of the topological string. That is right, but certainly these works, which were more tailor-made to make direct connection to Mirza Kahani's work, they aim for including this boundary contribution, and also they want to describe volumes of moduli space.
Okay, now that makes sense.
But
can you tell me where the shift is coming from? This is the part which I don't understand. The gamma U's.
Oh, where this shift is coming from?
Yeah.
Yes. Okay. I can give you a rough explanation of that. So let's forget about this term for a second, which complicates things, as you say. Then up to some normalization factors, there were Peterson symplectic form, and it gets a bit modified when you have a boundary. But if you don't have a boundary, this is essentially just the kappa 1 class, which you're probably familiar with. So there is a different basis of. So the kappa classes you can again also express in terms of the psi classes. But anyways, so at the end of the day, you also have a selection rule, which tells you, I mean, as you pointed out before, I should view this exponential as just as a formal expansion of all these forms. And then there's a selection rule, which particular degree of forms are picked out by this integral, right? Now, if you replace this by a kappa 1 class, then essentially the type of correlators you're looking at in the topological gravity context look like this. I don't know, say D1, D2, tau, dk. So if this term here is absent, or this insertion, well, this term here is absent, then you have the usual topological correlators generated by F. Now it turns out the insertion of this term can be realized just by such a shift. So it's, in a sense, it's and you can understand it in the following fashion. So I'm getting a bit ahead of my time. Essentially, by introducing this overall class, inserting this overall class in the correlator, it just amounts to expanding your generating function around a different point in this formal space of parameters tks, and this is where the shift comes from. So this shift essentially describes the insertion of that particular class here. Did that answer your question?
Yeah, great, thanks.
Hans, I want to ask something. This formula for Vg plus 1p, on the right-hand side, there is no genus. So where is the genus information on the right-hand side of the formula?
You mean here?
Yes.
Yes, good. So yes, so actually, yeah, so this is yeah, so this is still a sum. Yeah, okay, so this formula, a good point. So this is formula is not, so this is so there's a formal sum over the GS, and this actually comprises already, so yeah, so so you have to pick the coefficient. Yeah, thank you for pointing this out. You have to pick. So this is a well, this is not quite correct what I said. So you have to pick the coefficient also at genus G. So this already comprises a full series of contributions at all genera. Yes, thank you.
Okay, thanks.
So just think of it as a function of GS, right? I mean,
yeah, exactly. Yes, yes. So it's the same GS that we have here. So what I've written, you have to pick out the corresponding contribution of GS if you really want to extract that particular one. Okay, good. So back to the Kdv hierarchy. So let me define the derivative with respect to TKs in the following fashion. And then there is something which is called in the literature a tau function. So the tau function is essentially just obtained from this generating function by taking a second partial derivative with respect to T0. And then the nice thing is this is this Kdv hierarchy where the if you just if you set the higher TKs to 0, this is where the name comes from, just gives rise to the Kdv equation essentially. So then the upshot is if you take the case derivative of this function u, of this tau function, then this can be expressed in terms of a certain class of polynomials. And these polynomials, they just depend on derivatives with respect on u and their derivatives with respect to T0. And it tells you that the case derivative of u is given by this particular form, where now these polynomials, you can compute them recursively. They are called Dickey polynomials. And you can also, well, the first few are explicitly given. The first one is just u. The second one, which is relevant actually for obtaining the Kdv equation. By the way, they also depend on GS, the higher ones. Looks like this, and so on. And there's a recursion prescription how to get them. I should also say to leading order at k, or in other words, when you set the higher genus information to 0. So the subleading terms are always of higher genus. This is the leading order behavior, and they can be computed explicitly. And so this is a very intriguing set of equations, partial equations, and reflects this integrability structure which underlies these topological correlation functions. But the nice thing about this is, if you think about this a bit or spend some time thinking about these functions, you can actually solve them. You can actually solve these functions recursively, and get also recursively in going to higher and higher genus due to this behavior. Unfortunately, I don't have time to go into this, but the upshot is that you can calculate as a genus expansion, as an expansion in GS, using this set of formulas, these functions explicitly by using some initial conditions. Okay, so now what I would like, however, to point out here are two things. So the first thing is that these functions, these partial differential equations, there is only a dependence in this equation star. So star depends only, equation star depends only implicitly on the TKs, namely only in terms of their derivatives. So and what you immediately conclude is that when TK is a solution as a consequence of this, then a new generating function G shifted by delta is also a solution, where we define this a bit more generally as delta K plus TK, where these TKs are some constants. Okay. And a particular case we have, a particular instance we have already spelled out. So the upshot is that the generating function of these topological correlation functions is a solution to the Kdv hierarchy, but also this this shifted generating function of the correlation functions in the context of JT gravity is also trivially, by this fact that there is no explicit TK dependence in these equations, is also going to be a solution of the Kdv hierarchy. Okay. So this allows me now to actually phrase the proposal, or one of the central proposals we make in this work, is that module some caveats which I'm going to mention, or that what you might ask for, is that the solutions. So we propose that the solutions of the Kdv hierarchy, the space of solutions of the Kdv hierarchy, corresponds to JT gravity deformations. And in the remainder of this talk, I would like to give evidence for this proposal, and I would like to convince you that there is such a correspondence. So the caveat, let me already spell it out here, but it will come back time and again. The reason why such a proposal is actually difficult to formulate in its full strength, because remember, we are saying that the deformations are essentially given by such quantities delta K here, but this is an infinite number of constants. So we are talking here about infinite dimensional spaces. And certainly in order for this correspondence to have a meaningful formulation, you should also impose some conditions, some growth conditions on these parameters delta K's, such that you still get a sensible JT gravity formulation. And I will try to make this a bit more precise, but I also have to admit a precise formulation, how this space is precisely formulated and what classes of deformations, in particular, when you start deforming infinitely many, I mean, when you start deforming, further deforming this generating function by an infinite number of constants is still an open question. Okay, so in order to illustrate our point, so let me come first to the JT gravity deformations that we could take a look at. So we have the action of JT, and we want to now perturb this action by additional terms. And there's a particular simple term that we can add, which is of the following sort. And there is a motivation for looking at this particular deformation. So first of all, this is designed such that it does not change So the asymptotic boundary is not affected. And this was actually also the motivation to study such deformations by Maxfield. By Maxfield and Turiachi, and also in a paper by Witten. Also, where this is a particular nice deformation because it has a nice interpretation. So if you add this particular term to the action, then what you find that this modifies the constraint that came from the equation of motion with respect to phi. So before we said we had a constraint that the curvature had to be set to -2. So this is now modified in the presence of this term in the following fashion. You have a finite number of points where you have actually delta-like delta function-like curvature singularities, where and this is also something that has been discussed in these papers, but in particular, this also has been pointed out, this interpretation by Mertens.
What determines K?
Hold on 1 second.
How do you get this summation? And
okay, good. So yeah, so K you actually have to when you work out this, I mean, remember, notice this is a funny. I'm also a bit schematic here. This is really, I have to. This is not quite the action. I should write the Lagrangian here. Let's be precise. So you have an exponential modifying the Lagrangian, and now again, when you treat this in a perturbative way, you expand this out, and then you get contributions from various powers of. I mean, if you treat this in a perturbative fashion, you get contributions from various in the Taylor expansions from various terms, and this corresponds to the case term. And then you're still left with when you do this on the path integral level, you're still left with an integral over the positions of these xi. So essentially, what this is telling you is you should now be summing, and I illustrate that in a cartoon more explicitly in a moment. You should be summing now over all Riemann surfaces where you have an arbitrary, or say k number of points where you have such delta function like curvature singularities. So so this is at all possible positions. And for arbitrary k. Okay. So it turns out that in for a technical reason, but it might also be a conceptual reason, that we want to limit this alpha in a particular range. And what is this alpha? This alpha actually, if you have such a delta kind of singularity in curvature on a Riemann surface, the way you can interpret this is that you have actually a conical singularity at this place. So you have conical singularities, and this this alpha is the identification angle in this conical singularity. So the cartoon is, we have on this surface something like this. And this now becomes, if you cut this open, it becomes in this hyperbolic geometry some wedge. And this wedge comes with an angle. And this angle is alpha. So in other words, what we are saying here is that this characteristic parameter alpha here geometrically corresponds in this context to this to these particular geometries. Now, what is nice is that actually we can now again tackle this moduli problem, including these conical geometries. So that's what we want to compute, and this is what we discuss in detail in the paper. Is we want to compute now this partition function, which depends on the coupling strengths epsilon and on alpha in JT. So we want to compute this partition function, which is now also depending again, it's same setup, just that we allow for these conical singularities. And then again, there is this leading term that we had before, and then there are the individual contributions, epsilon alpha, which now depend on these two quantities and on beta. Okay, so this is now, as was asked, I mean, what is this K? So this is now kind of becomes a fairly complicated sum. I mean, what is the sum? Well, at genus zero, or at the disk level, I mean, we have this disk contribution. Then we have at the order epsilon. So epsilon serves now, we have such a contribution and so on. And then at, say, genus 1, it keeps going like this. We have the standard genus 1 contribution. And then we start adding these sparks here. And like this, okay? And now the upshot is that we can actually carry out this sum, or this sum can be evaluated again, because there are also formulas how to express again in terms of certain integrals these volumes, including conical singularities. And the upshot is that the result of this analysis is that the corresponding generating function, which plays the role, is again given in terms of a Kdv solution. And in particular, the Kdv solution we should be looking at is that it's a deformation of the JT gravity Kdv solution in the following fashion, that there's an additional shift, where now this shift, delta K, can be explicitly spelled out. It depends on this identification angle, as it should. And it also depends on this coupling. Epsilon K factorial. So now this is the simplest deformation that I tried to sketch, where you can include such a simple defect species type. Now you can play the game and include actually several species type, namely with several parameters epsilon and alpha, with different parameters in epsilon and alpha. And again, you can carry out this, and this will again lead to yet other solutions of this Kdv hierarchy, which introduces for each species type an additional shift contribution. So, so if you allow now for an infinite number of different species, you can actually also allow for, you can actually even flesh out part of that infinite dimensional deformation space that I try to formulate in this general proposal. So by increasing this number, or even writing an integral over, as has been also considered by Witten in one of the paper, generalizing this to an integral over a continuum of deficit angles, identification angles, we can actually flesh out a fairly rich structure of JT gravity deformations, and all these deformations turn out to be realizable in terms of solutions to the Kdv hierarchy. So there are generalizations which we discussed to some extent in the paper, but the last word has not been said in this context yet. So several, so possibly infinitely many, and maybe even not countable number of defect species. So then we'd have, on the one side, we can modify our action where this is some set, possibly some index set, where we can, on the JT side, realize a rather large class of deformations, and they all form solutions to the Kdv hierarchy. So this gives some evidence for our proposal. Now, I don't have time to talk about this, but on the matrix model side, I mean, these TKs, they also, this just also comes about when you look at the original formulation of Witten and Kontsevich in terms of the matrix model. And the matrix model side, the matrix measure can be also expressed in terms of these couplings TK, and then you actually can also work out, and this is something we also do in the paper, how these modifications, how these shifts actually implement on the matrix model side. So let me come in my, I'm a bit running out of time, but nevertheless, I would like to mention a few applications of this. So I talked today about a very technical part of the kind of computations that we can do, and I think these technical considerations are nevertheless important in this context, because it actually gives us some tools. I mean, by looking at the solutions to the Kdv hierarchy, actually to analyze various interesting physical questions. Some of them we also discussed a bit in the paper, but let me just point out a few. So there are these spectral form factors in this context, which contain a lot of physics, spectral form factors in the context of this holographic duality. And they arise from an analytic continuation of kind of a correlation or a partition function with two boundaries, where you introduce the following analytic continuation. So you have, so this follows from, you have now geometries with two boundaries. So you have geometries like this. I mean, the tree-level geometry, something like that. And you have two inverse temperatures coming from the two boundaries. And then you can also play this game. Then there are these higher genus corrections, and so on and so forth. By the same techniques, you can also compute these quantities. And if you analytically continue by introducing such a tau here, which is interpreted as time, you get the spectral form factor. And then in this context, the spectral form factor has characteristic features where we could say a lot of things about. But when you look at the spectral form factor as a function of time, so the characteristic feature is something that you encounter is of the following sort. You have a certain a piece which is called a slope, and then you have a ramp, and then you have a plateau. So actually, Joshua, who is part of this collaboration, I mean, he knows all the gory details about the physical features, about these spectral form factors. I must say I'm not such an expert on this, but the interesting feature from this technical computation that I presented here is you can now analyze all these features that show up in this context as a function of these deformation parameters. So here we can analyze the spectral form factors as a function of deformation parameter sigma. And the other thing, which is both a conceptual thing, but also a computational challenging thing that I would like to point out. So at present, right now, what we discussed is that we looked at the Kdv hierarchy we looked at formal solutions in the string coupling GS. So this is nice if you want to pick out particular correlators of JT gravity at a given order in this genus expansion. However, as has already been pointed out in the original proposal by SSS, but then also you should compare with this discussion by Clifford Johnson. So he has very nice papers on this. This is actually not the end of the story, because for this more physical application that we have in mind here, we don't want just not just a formal expansion, but what you would also like to include are non-perturbative effects in e to the 1 over GS. These effects now render these asymptotic expansions that we have been talking about, these generating functions, actually as convergent. And from a physics perspective, you need these effects GS. And there's also a discussion, particularly by Johnson, about where these effects come from and what structure they have, and so on. But so in our context, it would be nice to have for the physics application to get a handle on this on these solutions, including these effects, not just as formal solutions. And actually, it's said that or discussed in the literature that this plateau feature here, I mean, this transition from ramp to the plateau, actually makes it necessary to have these 1 over GS factors. However, it turns out that in a low temperature expansion, and this was also something already pointed out by Okuyama Sakai, you can actually work in a certain limit where these non-perturbative effects are suppressed and where this asymptotic series actually becomes convergent. We nevertheless encounter that this plateau arises, including also all these deformations that we can discuss, even in the absence, or at least where these effects are scaled to 0. So this raises the question whether the plateau is maybe not a feature of the 1 over GS effects, but maybe the plateau is actually a feature of being Borel summable. And there's a particular limit where actually the series becomes summable. And there we also encounter this plateau. So this is certainly, if you go away from this weird limit, intricately linked to the 1 over GS effects. But our suspicion is a bit that, and this is something we're currently also investigating, that this plateau is actually a fact, arises from the fact that we can actually this is not just a formal sum, but a convergent sum, and not directly linked to the 1 over GS effects. Okay, sorry, so there are other applications.
I just wanted to. So you're saying for the large tau, you have the series will converge. Is that the statement?
No, the statement is the following. So, the statement is the following. So, so a priori, we can compute this function in a similar fashion as we computed this previous function with one boundary. And however, a priori, this is a formal expansion in GS. Okay, so you could say, okay, so the leading contribution, as in a quantum field theory calculation, the leading order contribution coming from the disk is the leading order contribution, and then you can add finite contribution at each order, which correct that result. Fair enough. But if you take into account all corrections, it diverges. Okay. So if you want to extract this thing here, it turns out that you get this characteristic shape, which is expected by from general considerations if you have this ensemble of quantum mechanical systems. But you get, and this is for various reasons expected, so you get only this result if you can carry out that sum correctly. Now, Okuyama and Sakai they pointed out that there is a low temperature expansion that you can do, where actually it turns out that in this, so this is again a funny limit, there's a certain double scaled limit. In this double scaled limit, all these e to the minus 1 of GS corrections, which you have in that, if we had the full-fledged partition function, including these non-perturbative effects, are actually scaled to 0. And in this limit, you can actually carry out this sum over genera exactly, and it also converges. So now we actually have a weird, admittedly a weird limit, where we have a handle on this function, where we have an exact expression in this function, and we can also do this, including these, this is what we contributed here, included these deformations. And then if you plot this function, you find this particular characteristic behavior. However, it's discussed in the literature, where does this behavior come from? And in particular, the transition from the ramp from the plateau is typically discussed to be attributed to the 1 over GS effect. So now what I'm trying to say here is that since we're observing, and also already Koyama Sakai, this feature already where these effects are actually scaled to 0, there is a possibility that it's actually related to the Borel summability of that theories than rather to the 1 over GS effects directly. I mean, this is just an observation that I'm mentioning here, and that we are currently exploring. I mean, this is not the final word yet, but this sounds, at least to us at the moment, a plausible explanation, that this is not necessarily a feature directly of the 1 over GS effects, but rather a feature of being able to carry out the sum over all genera. And sure, if you don't take this funny low temperature limit, then this is related to the, I mean, if you want to make this series Borel summable, you need to include these effects. So it's closely tied together, these two statements. Okay, so I'm already a bit over time, so maybe let me stop here and take more questions.
Thank you for this great talk. So time for questions. So actually, I have then a question about. So there's a variant of this JT gravity construction where you have this end of the world brane, and so you put them on some line where the K is in extrinsic curvature vanishes, and there is some tension of the brane, and then this model was explored as black hole microstate model in a paper by PSSY, and it was shown how the islands come about when you do the similar kind of summations. So so there they use something like a resolvent technique to do this. At least at the planar level, they could sum over all planar things, and we were able to get this resolvent, and that was a technique they used. So do you think some generalizations of that kind, like if you put end of the world branes or it could be pursued in this setup or in your method using this recursion relations?
Okay, so there are okay, so I've heard of the works you're mentioning. I must admit I'm not very familiar with them. There are two things I can say to this. So certainly the part that I haven't talked about, if you do the matrix model ensemble computations, you use matrix model techniques, and you also employ resolvent techniques that sound very much what you've been mentioning. So there could certainly be, I mean, it sounds to me that there certainly could be a connection. Now, the other thing that I want to point out is, and maybe this is related, I don't know. There is, and this is also something we are momentarily investigating a bit, is the following, that I mean, in particular, also when it comes to these non-perturbative effects, I mean, they look like brain effects, and there is also a connection that I also haven't pointed out to minimal string theory in a certain limit. So you can interpret this theory as minimal string theory of the 2, p minimal string theory, where you send p to infinity. And what we are now currently investigating or aiming to investigate is that you might impose other boundary conditions which come from these, and this is also already discussed. There you have in these minimal string theories, you have these FCCT brains and CZ brains and so on, which are already discussed in this work by, I mean, the various works, but it's also already mentioned here that this should be relevant to these effects. And to this end, indeed, you would have to discuss, and we are not so sure what this now means on the geometric side, these brains, but you certainly would have to discuss Riemann surfaces with new boundary features, with new types of geometric features that we are currently trying to explore. And maybe this could sound like something also you're mentioning, that there is additional ingredients that you can implement, and maybe along the lines that you've been mentioning, there is indeed a more direct connection. I don't know.
Yeah, so there they were actually having some end of the wall brain states, and they were looking at matrices. That they're taking summing over them, and looking
so
at
is that on the resolvent side? Is that like inserting kind of determinant like operators, something like that?
Could be.
Okay, so this is very interesting.
Yeah, so essentially they were able to get
because on the matrix
like that,
because on the matrix model sides, I mean, as is familiar from discussion of Ishibashi states or something in this boundary conformal field theory techniques, you describe these kind of brains. I mean, at the end of the day, these minimal string theories, there's a CFT formulation. You describe these brains in terms of such determinant kind of, or this, or exponentiated trace insertion and stuff like that. And there you are indeed using these kind of resolvent techniques that you've been mentioning. So that sounds very much connected, yeah.
Okay. Thanks. Yeah.
But sorry, I'm not aware of that setup you're describing that I could give a more specific answer.
Yeah. So basically, what they do, they introduce states on this end of the wall brain. So they have in state and out state, and then they trace over that, and you can have like several copies. And
I see. I see. And these states sound like boundary states in a conformal field theory language.
Exactly.
Right? Yeah,
exactly. So you're tracing over boundary degrees. Yeah. Exactly.
Okay. Interesting.
Okay, so thank you, and perhaps more questions. Okay, so I guess let's conclude today. And thanks, Hans. And you should visit us in Chennai. And
thank you.
Okay,
Hans.
I've never been to India, I must say. And
so you should.
So then the pandemic came, and so I had planned actually to travel to India, and but maybe, yeah. So hopefully this will end at some point.
Yeah, hopefully, yes.
So how is the situation at your university?
What?
Yeah, I end the recording now.